Yeah, so today I want to become a bit more concrete. So last time I gave kind of survey what we want to do. We want to understand somehow data in high dimensions and functions acting on the data. And the functions should be like neural networks, specific form of functions. Okay, but the main thing which we first should understand is how sets in high dimension behave. Or we have the data sets, and we want to make statements about them. And those statements will typically be a kind of probabilistic statements. I mean, we don't have statements which are true for all our variables which we consider, but for most of them. And this means, of course, we have to specify how do we measure the probability or the size of our sets. And of course, yeah, we will do this essentially by probability distributions. Okay, and maybe the simplest one is to take just a uniform distribution on the set, which just is the volume. So I mean that's the easiest thing. If I have a data set, how do I measure its size? The easiest thing is just to take the volume of this set, the volume in our R to the P. Okay, and then of course I have one data set in which I'm interested, all the data I consider, and then I'm asking which of them have given properties. And then of course the probability is the ratio of the two sets. And of course I need somehow, I have to normalize, for probability of course I have to normalize things. So the whole set I consider, this is the volume by which I normalize. And of course this means I cannot talk about all elements in R to the P, because the volume is infinite. Okay, and this is also, of course, is a reason that maybe it's better to consider other probability distributions which can extend to all of R to the P, and this will be Gaussian distributions, which of course are also relevant from many other aspects. Okay, so, but first we should get a feeling how do volumes in high dimensions behave, because they behave quite strange. Okay, maybe if you have worked with them, you have a feeling for them, but if you have never thought about high dimensions, some things are indeed a bit strange, and we should get a feeling for this. Okay, so what we want to talk about are volumes of, we are looking on specific sets where we really can calculate things, and those are essentially balls or hyperballs, and maybe also cubes in high dimensions. Okay, so we are talking about volumes of hyperballs. I mean, hyper just means it's high dimensions. Very often I just say balls. And cubes, hypercubes. But the main focus is how do they behave in high dimensions. And then in particular, we want to see the feature which will be one of the driving ideas of the whole stuff, namely that we see concentration. So namely properties in high dimensions concentrate, or the volumes concentrate at specific places. Okay, so in high dimensions, and where they concentrate. I mean, concentration is one of the big things which we should better understand. And here we can see things somehow quite explicitly. Good. Okay. So I mean, what we want to understand are, let's say, sets in R to the P, P dimensions, and A is some set. Let's say our data set, and we want to understand this for P is large. Okay, and we want to understand the typical or maybe the average behavior, and in particular also how big is the difference between the typical and the average behavior. Okay, and so as I said, we describe our sets by probability distributions. So I mean, we are not interested in one particular data, but we are interested in a collection of sets, and we want to understand the behavior of those elements in a typical or averaged way. Okay, so we need a way of talking about probability. Probability distributions in R to the P, and now the most basic one is somehow if I take the uniform distribution on a set which I consider. Of course, then the set should be bounded so that the volume is finite, and then I can take this set and ask about subsets of this and compare the volume of the subset with the volume of the whole set, and that's essentially the probability of the subset, or of the property maybe in which I'm interested. Okay, so the distributions which I consider at the moment, it's a uniform distribution on our sets, and this is just the volume. I'm just measuring the volume, the usual volume integration with respect to the Lebesgue measure. Okay, but that's the volume of our sets, and then later we will consider also Gaussian distributions. Okay, because in many respects Gaussian distributions are somehow maybe more important and also more easier to deal with. Okay, so we will have to understand quite a bit about Gaussian distributions in R to the P, but for the moment we do the uniform distribution. Yeah, because essentially this is just ordinary integration over sets, and at least for balls and such things we can say quite a bit about them. Good, okay, so this means, so what do we consider? So if I have such a subset of R to the P, so P is always my fixed dimension, which of course I consider for large P, or somehow P should go to infinity. Okay, so we consider the volume, or maybe a bit more mathematical terms, the Lebesgue measure of such a set. So I denote this, let's say, by volume of A, and of course, how is it given, or what is it, or how can I calculate it? By integrating over the set. So I mean, I'm integrating over the set with respect to dx. So this is p-dimensional integration, or maybe can also say I'm integrating over R to the P, but I'm integrating the characteristic function of this set. So the function which is 1 on the set and 0 outside, and dx. Okay, and integration in high dimensions, of course, is a nice theory and it works, but the important thing is how do I calculate it, and I calculate it via Fubini, via iterated integration. So I think everybody knows how to integrate in high dimensions. So this is nothing else than a iterated integral of my P coordinates, and I have to integrate over the set. So I have, usually I denote the coordinates by my vector by t1 up to tp, because I don't want to use x with a subscript as a component, because I will later have several of my x's. Okay, good. Okay, so I write the vector x, I write it as t1 up to tp. So those are the components of this vector. Okay, and I'm only integrating over the set A. And I'm integrating with respect to my p variables. And of course, I mean, depending on A, okay, one has to see how one can do this integration. Okay, but in principle, everybody should know how to do this in principle. Okay, and now we want to look on specific sets, and the two sets, which I already have in my heading, is the ball and the cube. Very easy sets. And I want just to calculate their volume and see how it depends on the dimension. Okay, so we consider in particular the ball. I denote this by B, put the dimension here, and then of course I can take a radius, capital R, that's the radius of my ball. And so this is nothing else than the vectors in R to the P, so vectors x, where the components are denoted by T1 up to Tp. This is an element in Rp, and that's the ball. So this means the sum of the square of all the coordinates has to be less than R squared. So the length of the vector should be less or equal to R. R is the radius. Okay, so this means I have T1 squared plus Tp squared should be less or equal to R squared. And of course this here is the norm of my vector squared. Okay, that's the usual Euclidean norm of my vector. Okay, so that's the ball, or the p-dimensional ball or hyperball of radius r. Okay, and I consider here balls about the point 0. Of course, I could shift it to somewhere, but it's good enough to look on this one. So this is the p-dimensional hyperball, but usually I just say ball of radius r. Okay, and that's the main guy of which I want to calculate the or talk about the volume, but maybe let me also write down the hypercube, which is somehow easier, in particular if I want to calculate the volume. So namely the hypercube, I denote it by C, also depending on R, which is now not the radius, but it's the side length, but I start at 0, so this has the length 2R on the side. Okay, so this means this is just the product of each coordinates, where each coordinate is just between plus and minus R. So this is just the product of the intervals from minus R to R. So it's again the cube centered at the point 0. So I have this p times. And this, so this of course is just again a vector in R to the p with components t1 up to tp in Rp, but now my constraint on the components is just that each of them has to lie between plus and minus R. So the condition is that the absolute value of Ti is less than R for all I from 1 to P. So that's the hypercube, p-dimensional hypercube or cube. And the side length is 2R. Because I mean 0 is in the middle, and then I go R to 1 and R to the other side, so the length is in each direction, it's 2R. So this is the p-dimensional hypercube. Of side length 2R. Good, okay, and maybe let me just draw a few pictures. Yeah. Okay, so maybe here. So for the dimension, of course, I mean, drawing pictures I can only do in very small dimensions. And of course, those pictures are usually misleading for high dimensions. But nevertheless, maybe just to make clear the distinction between the cube and the ball, maybe let's draw it in 1, 2, and 3 dimensions, where at least I can do a little bit. So here's the cube, and here's the ball of radius r. And in p equal to 1, I mean it's just an interval, and both are the same. This means just one dimension, and I just have distance r from 0. So the cube is just the interval from minus r to r, and the ball is the same. Okay, so in dimension 1 there's no difference, but of course in higher dimensions they are not the same anymore. And of course in p equal to 2, I mean the cube is just a square. 0 in the middle, and of course I mean this here is r minus r, r minus r. Yeah, and the ball in 2 dimensions is the disk, the interior of the circle of radius r. Okay, and then in 3 dimensions, okay, the cube is really the cube. With 0 somewhere in the middle, and then I mean, yeah, the side lengths, each of them are 2r, and of course here I really have the ball in 3 dimensions of radius r. Good, okay, but then for higher dimensions, of course, maybe it's not so clear anymore how to draw pictures. Maybe some people can draw 2-dimensional projections or 4-dimensional cubes or high-dimensional one, but it's okay. It's hard really to get, to really see what they mean and how they look like. Okay, but what we can do in any case is to calculate volumes of such guys. Okay, because I mean we have this formula, and this is of course quite clear how to deal with it. Okay, and of course the volume of the cube is trivial, because I mean the volume, I mean that's more or less the definition of how you define volumes. You define what is the volume of a cube or a rectangle. It's just the product of the sides, and then the rest you approximate by this. That's how you do integration in high dimensions, essentially, or how you define the volume. Okay, but so the volume of the cube of radius r. So this is, of course, is just the product of all the sides. I have p sides. Each of them has the length 2r. So it's just 2r to the p. Okay, and this means in particular, of course, if I want to have a nice behavior of the volume, I should take the length equal to 1 of the sides, which means r should be 1/2. Okay, and then I have a unit cube and which has volume 1, and it has volume 1 in each dimension. Okay, so the unit cube is trivial. In any dimension it has volume 1. That's more or less, I mean, the normalization of my volume. Okay. So in particular, the volume of the cube where r is equal to 1/2, then 2r is equal to 1. This is 1 for all p. Good. Okay, but now more interesting thing is how about the hyperboles of radius r or of radius 1. Okay, so how does this behave in high dimensions? Okay, and of course we can just do the integration. We can calculate it. And maybe you have done it before, maybe in some analysis class or so. I mean, this is something which once in your life you should do. Okay, but I'm not sure whether I have done it before, so I'm doing it here now. And then we will see and try to understand the behavior in high dimensions. First of all, maybe one should observe how does it behave with r. Of course, I mean, the cube goes with the radius to the power p. I just erased it. And that's clear. And so, of course, the ball should be the same. But maybe we just should check this. So what is the volume of the ball in dimension p of radius r? So by definition, of course, this is the p-fold integral over the components of my vector, which satisfy t1 squared plus up to tp squared less or equal than r. And I have to integrate over dt1 up to dpp. Okay, and now I can rescale this to the ball of radius 1 by essentially writing the t's as r times s. So I can also say this is the same as the integral, and I write now the t1 as r s1 squared plus, and I write the tp as r times sp squared. This should be less than, of course, here r squared, less than r squared. And my integration I can, of course, also do in terms of the s instead in terms of the r. So t is just r times s. So I'm integrating here with respect to d rs1 up to d rsp. Okay, so the r's are just coming out if I'm changing from integration from t to s. So I'm just getting, so for each change of the variables from t to s, I get here a factor r, so I get the r to the p. And then I'm left with the integral, which I now write in terms of the s. And of course, you see now, of course, I have an r squared here everywhere. So I can cancel this with this, and I get the condition that I'm in a unit ball. So I'm integrating now over the s's, where s1 squared plus sp squared is less or equal 1, ds1 up to dsp. And this is now the volume of the unit ball, because now I'm integrating over a ball of size 1. So this is the volume of the unit ball, and so the difference between a ball of size r and the unit ball is r to the p. I mean, as it should be. I mean, the volume scales with the pth power in p dimensions. Oh, okay, but this is shown by this simple calculation. So the volume of the ball of radius r is r to the p times the volume of the ball of radius 1. Okay, and so maybe it's enough to understand the volume of the ball of radius 1, and maybe instead of bp of 1, I just write bp. With this I mean that r is equal to 1. So I put bp without explicit mentioning of the radius. This should mean that I consider the radius 1. Okay, and now of course we want to calculate the unit ball. Okay, and so what is this? Of course maybe we can do it for we know it of course for small dimensions. Okay, so the volume of course of B1. So this is the interval from minus r to r, or maybe if I write it as our integral, this is integrating over dt1. I only have one variable from minus 1 to 1, and of course this is 2. So this is the interval from minus 1 to 1. The volume of B2, okay, maybe of course that's the disk, the volume of the disk. Of course we know this, but maybe let us do the integration and see, because okay, we want to get an idea how to go to higher dimensions. So what is the volume of the B2? So this is the integral, of course the double integral. Now I'm integrating over T1 and T2, which satisfy T1 squared plus T2 squared should be less or equal to 1 dt1 dt2. Okay, now we can do the iterated integration. We first integrate T1, or let's say we integrate first T2, and of course this can run from minus 1 to plus 1, but then depending on D2, the T1 has to satisfy this condition here. So the T2 has to run between plus and minus square root of 1 minus T1 squared. Okay, so the second integration goes from minus 1 minus T1 squared up to plus 1 minus T1 squared, and I'm integrating over T1 and T2. So I mean here I have written the integration domain just as a description, a constraint on the t's, but now I have really written it as an iterated integral, which I really can then do one after the other. So I mean I'm just integrating here. If I integrate over this, I first integrate over T1, and if T1 is fixed, I'm integrating for T2 over this. So this means, that's the usual Fubini integration. Good, okay, and now, so the first integration, of course, I'm integrating the constant function 1. This is trivial, but I get now a non-trivial thing from the boundary here. So the first integration, which I'm getting here, so this is, I'm integrating from minus this to plus this, so I get twice this term, which is 2, and then 1 minus, and T1 I call now just T, so the square root of 1 minus T squared dt from minus 1 to plus 1. Okay, now I'm back to a one-dimensional integration. That's one which we can also do by changing the variables to sign or something like this. I don't want to do this, but if you do this, you just get pi, which of course is the area of the unit disk. Good, okay, but you see, I mean, if I want to iterate this here, maybe, okay, it's not so nice, and actually it's much better, I mean, to do the integration over a circle in polar coordinates, because this is much more adapted to the situation. So maybe let me do this, because then I really can do all the steps very easily. And this is also how I will address the higher dimensional situations. So the same calculation again by polar coordinates. So beta by polar coordinates, which means instead of t1 and t2, I consider the radius and the angle r and phi. And so I'm writing t1 as r times cosine of phi and t2 as r times sine of phi. So I mean, I'm going into polar coordinates. So if I have here my point t1, t2, I write it as r times cosine phi sine phi, where phi is here the angle and r is the radius of this point. And then of course this integration over t1 and t2 can be rewritten by the usual transformation formula for the polar coordinates by integrating over r and phi. But of course we get the change of the volume element. So instead of dr d phi, we also get an r. Okay, so the integration over t1 squared plus t2 squared less or equal 1 dt1 dt2, which we have to do, and which we can do by iterated integral. Okay, I mean that's Fubini. Do iterate your integrals, but the other thing you usually use for calculating integrals is to go over to make a change of coordinates. And here we are changing it to our polar coordinates. And I mean the function doesn't change. This was the function 1, but now we are integrating over dr, dr, d phi. That's the change the formula. And of course we are integrating now. I mean of course now the condition that we are inside the circle becomes very easy in terms of the radius. I mean that's why it's a good idea to use the polar coordinates here, because this condition here just tells us that r is less or equal 1 and phi has no constraint, because I mean it's symmetric in phi. So we're integrating the radius from 0 to 1 and the angle from 0 to 2 pi. And these are now integrations which we can do very easily. So I mean, phi is not showing up here, so the integration over phi just gives us a 2 pi. And so of course you see where the pi is coming from in the final result. And the integral over r, I mean, we have now here an r, so it's not the constant function anymore, but we have to integrate over r. But of course, we can do. That's 1/2 r squared. That's the indefinite integral, Stammfunktion of r, and we have to integrate from 0 to 1. So of course this is just 1/2. Okay, and 1/2 times 2 pi is of course pi. Okay, so we see very easily how we get the volume. Okay, but that's things which everybody knows. We could now also maybe integrate over the ball in 3 dimensions, but let's now really do it general for higher dimensions. And the idea there is that essentially we do integration like this, or we reduce the p-dimensional integration by integrating out 2 of the variables in a very similar way as here, and then compare the p and the p minus 2-dimensional volume. So we derive a recursion formula for the volumes. Okay, so for general p, derive a recursion, and we do this by not integrating out 1 variable, but by integrating out 2 variables. So essentially doing what we did here, also in higher dimensions. And we integrate them out in polar coordinates. So by integrating out 2 variables in polar coordinates. Okay, so let us do this. So what we want is the volume of the unit ball in p dimensions. So the volume of bp, which of course is just in general the integral over our p coordinates such that they satisfy t1 squared plus up to tp squared is less or equal 1. And I have to integrate over my coordinates t1 and tp. Okay, and now I introduce again polar coordinates, but only for, let's say, for the two last variables. So I just change the two last t's into polar coordinates, and then essentially I can do the integration over them in a similar way as here. So I'm writing this as still an integral over p variables, and so the first two p minus 2 variables I keep the same, tp minus 2 squared, but for the last two I introduce polar coordinates. So in the subspace generated by the last two coordinates, I go over to polar coordinates. So I have an r and a phi. So I write this as, so I write the tp minus 1 as r times sine. So I get here r squared sine squared phi. And I write the tp as r times cosine. So I get here the square, I get an r squared cosine squared of phi. And this has to be less or equal 1. And now you see why it's a good idea to introduce those two variables, because I have here the sine squared plus the cosine squared, which is equal to 1. So the phi falls out in this constraint here in the same way as before for my polar coordinates. If I only, so I mean, it's much better to reduce it by 2 by doing this instead of trying to do a recursion in steps of 1. Of course, you can also do this, but this is maybe a bit more complicated. This here is nicer. Okay, so and then of course I have to integrate over my coordinates. So the t1 up to tp minus 2 are the same. And then of course I have replaced the last two by r and phi. So again I get the volume element, or the area element, with this integration. So it's r dr d phi. Okay, so that's as before. Yeah, okay, and now you see that I, of course, do this now in an iterated way. So first I integrate over those guys, I integrate over r and phi, and if they are fixed, then I'm integrating over the other ones, and the constraint which I have here is then a constraint, which essentially tells me that I'm in the p minus 2 dimensional sphere, but of ball, but of radius 1 minus r squared. Okay, so maybe let me write this here again. So I'm integrating here over the two last variables. So phi is running from 0 to 2 pi, and r is running from 0 to 1, because I'm in a unit ball. So I also have to be in a unit ball in a smaller dimension. Okay, and then I'm integrating over those variables. Then I'm integrating over the variables dt1 up to dp minus 2. And then I'm integrating over r dr and d phi. Okay, but now I have to write the condition for those guys, and you see, I mean, the condition for those guys is now that t1 squared plus tp minus 2 squared, plus r squared sine squared plus cosine squared, but this is 1, so it's just r squared, and the r squared I bring on the other side. So it's now really a condition in terms of r, so this is less or equal 1 minus r squared. And so now you see, I'm integrating here over a ball in dimension p minus 2, but the ball of size of radius 1 minus r squared. So this integral over the p minus 2 variables, so this is the volume in of the radius of the ball in dimension p minus 2, but of radius 1 minus r squared, and of course the square root of this. So this is the square of the radius. Okay, and now it's good to know that that in dimension p, how we scale with the radius, because now we really can write this here by what we observed before. This is just the radius to the power of the dimension, so to the power p minus 2. So this is 1 minus r squared. Then I take p minus 2, but here I have the square root, so it's p minus 2 to the dimension p times the unit ball in this dimension. So times the volume of BP minus 2. Okay. And so you see, if I do this integration, I get here something which depends on R. So I still have to integrate over this. But this volume here doesn't depend on R, so this just comes out. So you see I get as a common factor really the unit ball in dimension 2 lower. And then I'm left with a factor which I still have to calculate. Yeah, so I have. So this inner integral I calculated as the volume of the p minus 2 dimensional unit ball times this factor. Okay, this doesn't depend on R, so I can take this out of the integral. So this is the volume of the p minus 2 dimensional unit ball. Then I'm left with the two integrals over phi and R. Phi is not showing up anywhere in this integral, so I just integrate the constant function in phi from 0 to 2 pi, so this gives me a factor 2 pi. That's the integration over phi, and I'm just left with the integration over R. This is a non-trivial integration, but that's a quite easy one. So I'm left with the integral from 0 to 1. Then I have the R from the area element, and then I have this function here, which I got from doing the integration in the first p minus 2 variables. So this is 1 minus r squared, and I have the power p minus 2 divided by 2, and this has to be integrated with respect to r. Okay, and this is an integral we can do, because again, very nicely, I mean, we have here r squared, but here we have the derivative. So this is really okay, by the substitution, this is really an integral we can do in the same way as we could do it before for the circle. That's the nice thing. Going over to polar coordinates, you get here the r, which you need to do the integration over this guy, which has an r squared here. Good. Okay, so let us do this. So what is the Stammfunktion? The indefinite integral of this guy. Yeah, so this is essentially this here, 1 minus r squared to a power which is 1 degree higher. So this is p over 2 minus 1. So I just have here p over 2. Okay, but so then we have to correct things. So I mean, if I differentiate this, I get, of course, the outer derivative is this guy. And then the inner derivative is 2 times r and the minus sign. The r I have here, but the 2 and the minus sign I still have to cancel away. So I have to multiply it with minus 1/2 and and of course here I'm getting, okay, yeah, of course this factor also comes out. Okay, so let me see. I have to cancel away yeah, the inner derivative, minus 1/2, and from the outer derivative I also get the factor p over 2, which I also have to cancel because it's not showing up here. So I have to multiply it with 2 over p. Okay, so anyhow, the derivative of this is this guy here, and I have to evaluate this from 0 to 1. And of course the 2 goes away. And if I do this, so this at r equal to 1, of course, is 0. And then I get minus this at r equal to 0, and the minus goes nicely with this, so I get something positive, which is good because the volume should be positive. And if this is 0, this disappears, and I just get 1 over p. So this here is just 1 over p. And so you see, we get here in the end a very easy relation between the volume in dimension p and dimension p minus 2. Namely, I just have a factor 2 pi divided by p. Yeah. So 2 pi divided by p times the volume of bp minus 2. Good. Okay. So the volume of the p-dimensional unit ball is the volume of the p minus 2 dimensional unit ball times 2 pi divided by p. So the dimension p shows up. So it's not something which is independent of the dimension. And of course we can now iterate this here. Or maybe first, let's say, maybe let us use this to see that everything is okay. Maybe let us calculate the dimension of the unit ball in dimension 3, because that's also something we know. Of course, here we can reduce it to the dimension 1. So this tells us, for example, that the volume of the ball in dimension 3 should be 2 pi divided by p. P is 3 in this case. And then I have the volume of B1. B1 was the interval from -1 to +1, so the volume of this is 2. Okay, so you see I have 2 times 2. I have 4 pi divided by 3. That's the volume of the ball in 3 dimensions. Good, okay, but what we really want is, of course, a general formula for arbitrary p. And then, of course, we iterate this. So if I want dimension p, I go down to p minus 2, and then, of course, I can do the same going down to p minus 4, and I go up until at the end, depending on whether I started from an odd or an even number, I'm ending at 2 or 1. Or maybe 2 I can go down to 0 if I really interpret the dimension of 0 in the right way. Okay, so we just have to do this and see what we get. I mean, in each step, essentially, we collect the factor 2 pi over p. So you see we get a factorial-like thing in the end. But we are going down in steps of 2. So it's a bit more tricky. It's not just ordinary factorial, but it's close by. Good, so let us do this iteration for general p, and then, okay, maybe we should distinguish the case where we start at an even dimension or we start at an odd dimension, because the formulas will be a little bit different. Of course, they are of the same nature, but it's better maybe first to distinguish them. Okay, so iterating the recursion gives what? Yeah, so let us start in even dimension. So write the p as a 2k. And then, okay, in the first step, I get a factor 2 pi over the p is 2k. So I have here 2k. And then I have the volume. And I'm going down in steps of 2. So I'm getting the unit ball in dimension 2, k minus 1. So k is just replaced by k minus 1. And I iterate this. So I get the 2 pi over 2k from the first step, and now I go down one step further, and then I get a 2 pi, and here I get the 2k minus 1. And then I'm left with the volume of, again, 2 dimensions smaller. Okay, and of course you see those 2's here cancel nicely, and essentially in each step I'm really collecting here a k minus 1. So here I really get the factorial, the usual factorial, but the one of k. Okay, so I mean, if I go down, so I can iterate this, and at the end, maybe I go down to 2, or maybe let's go down to 1. We just should think what is, or let's go down to 0. Okay, well, what is the volume of a 0-dimensional ball? Of course, this is nothing, but it's good to normalize this to 1. I mean, if you do this iteration going from 0 to 2, you see that the 0-dimensional ball should have volume 1. So you could also stop at 2, but in a sense, it's nicer to go down to 1, because then we do exactly k steps. So if we iterate this, so in each step, you see we are collecting a p over k, and then the k is getting smaller. So we get, if you do k steps, k means we are going down to 0. Then we get k factors of pi, and here on the bottom we just get k factorial. So we get p to the k, and here we get k factorial. But then we went down to b0. And of course, the volume of B0, this is something which we have to define, because a 0-dimensional ball doesn't make sense. So in 0 dimensions, we don't have volume. There's nothing, but this nothing should have volume 1. That's the only thing which makes sense. And of course, it has to make sense with our recursion, because I mean, we could stop at B2, and then we should have the same formula. So maybe if I do our recursion up to 0, then of course the relation between the volume in B0 and B2 should be the same as our formula, and the formula was, I have here pi, or what, I have 2 pi divided by P, but this is here 2, and then I have here the volume of B0. Okay, the 2 goes away. The volume of B2, that's a disk, that's pi. And here I have a pi, so you see I should define this as equal to 1. That makes sense. Then I can use my recursion also up to B0. Okay, but anyhow, so you see we have here a very explicit formula. So in principle, the volume is very nice. The very explicit formula for the even dimensional. It's very simple. It's just pi to the k and k factorial, and maybe let me write it in terms of p. I mean, 2k is our dimension, so this is the p. So what we have here for even p is the volume of the unit ball in this dimension 2k, or the dimension p. Let me write here p. So this is pi to the k factorial, but of course the k is p over 2. So it's pi to the p over 2 divided by the factorial of p over 2. Good, okay. But now we also should look on the odd dimensional case. In principle it's the same, but okay, the factors have to be coming together in a little bit different way. So it's because p over 2 is now not an integer number anymore. So I mean, also the factorial doesn't make a sense in the usual way. Of course, you have to interpret it what it means, and then you still have the same formula. But let us look on it concretely. So we have, now let me take an odd dimension and write it as 2k plus 1. So what do I have then? I mean, I do the same recursion. So the volume of the ball in dimension 2k plus 1, I compare this to the ball of a dimension 1 lower, and okay, I mean, whenever I do a step, what do I get as a factor? I get 2 pi, and now I have to divide here by the dimension, but so I'm dividing here by 2k plus 1. And you see, I mean, I can divide by 2, and but then I have k plus 1 half. Okay, in the next step, I will get 2 pi, and then I'm down to 2k minus 1, so I have to divide here by 2k minus 1. In the next step, I have 2 pi divided by 2k minus 3, and I'm going on like this, doing how many steps? K steps, and then I'm ending at 1 dimension. Okay, and so in the last step, I have here 2 pi, and I'm dividing it by the dimension 3. And then I'm comparing it with the volume of B1. And the volume of B1, that is 2. Okay, and so you see what I have here. Again, I'm doing k steps, so I get pi k times. So I get pi to the k. Okay, but then on the bottom, so if I divide by the 2, I get here again a factorial, but a factorial which starts at half integers. So I'm starting, if I divide by 2, I'm starting here at k plus 1 half. And then I'm going down in a step of 1, but the next is then of course k minus 1 half. And then k minus minus 3 half, and so on. And I'm going down up to 3 over 2, and maybe if I want the last one, I can also write maybe, okay, 3 over 2, and maybe let me add a 1 over 2, so 3 2. Yeah, so where do I start and where do I end here? Okay. Maybe, okay, so okay, let's say I'm starting at 5. Then I'm going to 3, and I'm going to 1. So what do I get? I get in the first step. So this is 2 times 2 plus 1, so k is 2. So I'm getting 2 plus 1/2, and here I'm getting 1 plus 1/2. Okay, yeah. Yeah, good. So I'm not sure why I should write here 1/2, so maybe not, but what? Okay. Okay, here's a 2 and the 2 is on top, so if I write it below, it's okay. Okay. So you see I really have the 1/2 here. And that's nice. I mean, if I would think of having a factorial, I'm going down up to the point where, okay, if I go down further, I would fall below 0. And that, of course, the last guy is 1/2. So this product here is really like a factorial, but starting at half integer guys. Okay, and so, I mean, those guys are coming from here, and this 1/2 is really the volume of B1, but written as 1 over 1/2. Good, okay, and so maybe if we collect things, so what do I have? Maybe if I want to write it as before I had p to the pi to the p over 2, but now of course I have here k as before, but now the k, this is not p over 2, but it's p over 2 minus 1. Yeah, okay. And so if I want to write this here as before, as pi to the p over 2, I have smuggled in a square root of pi, which I should cancel again on the bottom. So I can write it as, I mean, this here is exactly, this is p. So I have here p over 2 times p over 2 minus 1, and so on, up to 3 over 2, 1 over 2. But this here, I have made a mistake, because k is not this, but I have this difference, which is just the square root of pi, which I'm putting here. Okay, but you see, this here is essentially a factorial in p over 2 as before, but only p over 2 is not an integer, but it's a half integer. But of course, I mean, if I want to define factorials for arbitrary numbers, that's how I should do it, and that's how one does it. And in general, this is then called a gamma function. Okay, so I mean, I can define a factorial or an extension of the factorial from natural numbers to, let's say, all positive numbers, which of course is something like this. But you see, I have this extra pi here. It's a bit strange. This is then part of the factorial. But this fits together because there is a general function which is called gamma function, which for natural numbers is this guy, and which for these half integers is this guy. Okay, so this is I can really write this in a uniform way. Yeah, so let me write this here. But if you don't like the gamma function, I mean, you can take either this or this as I mean, this or this as the explicit formula. So let me write it in general for both odd and even p. For general p, the volume of the p-dimensional unit ball is given by pi to the p over 2. And then what is on the bottom, in the one case it's just this factorial, and in the other case it's also this kind of factorial, but with the addition of this pi, and this is what is the gamma function. So this is really the gamma function, and usually there's a shift of 1. So this is the gamma function of pi plus 1. And the gamma function, that's Euler's gamma function, which at integers and at half integers is exactly this, but which you can also define for general arguments with an integral formula. So maybe let me just write this down. I mean, it's not really important for us. What will be important is that we have an asymptotic understanding of this. I mean, that's Stirling's formula, which you also should know, which I recall, which is true for both cases. Okay, so where gamma is the gamma function, which goes back to Euler, gamma function. And we can just say, okay, it's for integer k, it's the factorial. For non-integer, half integer k, it's this other thing. So gamma of k is just k minus 1 factorial. And for the half integer ones, gamma of k plus 1/2. So k is here always in natural numbers. So it's this product in the factorial way, starting at k minus 1/2, k minus 3/2, going down up to 3/2 and 1/2, but then you have this additional square root of pi. Which, if you just want to define a factorial, looks strange, but maybe here you see why it comes into the game. So, and I mean, this makes sense to give this and this the same name, because you have a general formula, a very nice integral formula, which really specifies to those two situations. So in general, and there you can take arbitrary real arguments which are bigger than 0. A gamma function is defined as an integral. So gamma of s is the integral from 0 to infinity of t to the s minus 1 e to the minus t dt. Good. Okay. So I mean, that's just background. I mean, we don't need this. We essentially just need those two formulas, or what we really need if we really want to understand how these volumes behave. I mean, we have now explicit formulas, but they involve factorial quantities in a dimension somehow. And factorial guys are a bit, okay, not so nice to deal directly, but there's a nice formula in terms of exponential. I mean, what we better understand is exponential behavior. So, I mean, factorial guys behave in some sense like exponential. One can compare them with them, and that's Stirling's formula, asymptotically. That's the main thing which we need for getting understanding of those guys here behave for big dimension. Okay, so that's what we are going to use, which is true for all of them here. So that's Stirling. I mean, at least for the factorial. We should have seen this before. But this is also true for this gamma function, so it's also true for this quantity here. Okay, so Stirling's approximation for factorial. So this is actually approximation of the gamma function. Let me write it at s plus 1 for large s. So, I mean, s will correspond to a dimension, so that's what we need. And it behaves like 2 pi s, the square root, and then I have s divided by e to the power s. So that's Euler's constant. E and pi are showing up here, and s is the argument here. So it essentially goes like s to the s. Okay, for large s. Okay, and so this gives us then approximation for the volume. I mean, in terms of exponential things, which we maybe have a better feeling for. So this gives for large dimension for large p the approximation. So what is the volume of the unit ball? So the volume of the unit ball in p dimensions. So the exact formula is pi to the p over 2 divided by the gamma function at p over 2 plus 1. Okay, and for the gamma function we can now use this asymptotic expansion. So this behaves like yeah, so how does it behave like? Okay, I have this pi to the power p over 2, and here in the bottom I have, I mean, this is exactly, s is here p over 2, so it's exactly this here where s is p over 2. So I have 2 pi p over 2 square root, so this term, and then I have p over 2 and divided by e, so actually I have p divided by 2e to the power p over 2. Okay, or maybe if I write it the other way around, so essentially, what do I have? I have factors of pi to more or less p over 2, and I have e to this, and I have the p to this. Okay, so I have here, let me write it, 2 pi e divided by p to the power p over 2. So I have everything to the power p over 2. So I have here the pi to the p over 2, but then I have here an additional pi, which I should write down extra. So I have here the square root of pi. So that's taking care of the pi's. So this 2 here goes away with this one. Then I have here the e goes here, so it goes up as a p over 2. That's here, and also the p here. So this appears here, p over 2. But then you see I have here an additional p, which I should put here. So p. Good. Okay. So that's the asymptotic for large p. So this means the ratio of this and this for p to infinity goes to 1. Okay, so this just gives us an idea how the volume behave, and I mean they go somehow exponentially in a dimension, but it's a bit complicated, and maybe it's not directly clear even with this formula what we get. But so maybe let me write it down. And of course, I mean, if I have now a ball of radius r, then of course I just multiply this with r to the p. Okay, so in principle we have now exact formula in terms of the gamma function, and we have an asymptotic formula via Stirling's formula, which tells us how those guys behave, and we should now look a bit closer what this really means. So how do they really behave? So in particular, if p goes to infinity, I mean, what happens with this guy? I mean, the cube always of a fixed side length 1/2 had always volume 1. So if I fix here the radius of my ball, but the dimension goes to infinity, so what is with this? Does this explode? Is a constant, or does it go to 0? I mean, I have here essentially 1 over p to a high power of p. I mean, if p goes to infinity, I mean, of course, this goes to 0. So it's essentially like 1 over a small number to a high power. Okay, so this goes to 0. So the unit ball in dimension p, the dimension, if p is getting large, goes to 0. So the unit ball really, for very large p, has almost no volume compared to the cube. Of course, I mean, we have somehow, of course, we do a normalization somehow if we go between different dimensions, and our normalization is that we always say the cube, the unit cube, has volume 1. So we compare everything with the unit cube, but in high dimensions, the ball compared to the unit cube is shrinking to nothing. Okay, okay, you would say, okay, this is dimension 1, and of course the ball of dimension 1 is sitting inside the unit cube of size. No, not really. It's not sitting totally inside. Okay, but somehow it's compared, and the corners are going to 0. Yeah, but okay, but you might think, okay, so maybe if I make my ball bigger, then it is something like for the cube. If I take a cube where the side lengths are not 1, but let's say 2, then of course it grows exponentially. But if I take my ball of radius r, so what happens then? Maybe let me first write down what we know up to now and then think about this, but you might already think about this. So what happens if I have a radius r? maybe a very big r, but fixed radius, what happens with the ball of this radius? But first let me write down what we have seen up to now. So this is maybe, we call it a theorem. So what we just have proved, so the volume of the, let's say hyperbole is given by, and now I write it down with radius r. So what is the volume of the ball of radius r in dimension p? So the exact formula is pi to the p over 2, and then the gamma function of p over 2 plus 1. That's for the ball of radius 1. And then, I mean, if I have radius r, then I'm just scaling with r to the p, r to the dimension. Okay, so that's the exact formula. And of course, I can use Stirling again for approximating this, as we saw there. So what is it? It's 1 over p times pi. And then I have here 2 pi e divided by p. That's this here to the power p over 2. But now I also have an r. And I can also put it into this to the power p over 2, but then I should put here an r squared. R squared. And then the whole thing is to the power p over 2. Yeah, okay. And I mean, of course, this here is for p going to infinity. Yeah, and now maybe as a corollary, so what can we get from this? How does the volume behave? So how does it behave if I'm fixing r? So what happens then? Is it still shrinking, or is it exploding, or? I mean, if the r is fixed here, this r is of the same nature as e and pi and 2. I mean, this can be very big, but I mean, in the end, p is always getting bigger. So this ratio is getting smaller than 1, and then I still have powers of this. So I mean, the volume of the ball still shrinks to 0, independent of its radius. Okay. So maybe I have to go higher and higher in the dimension to get it really small. But any ball of a fixed radius in the high dimensions goes to 0. That's a bit strange. I mean, it's at least in our small dimensions where we are living, that's not maybe what we would expect. Okay, so let me write this down. So what we get from this, okay, so it's not only that the unit ball, but the ball of any fixed radius, so for any fixed radius r bigger than 0, the volume of the ball of radius r in dimension p goes to 0 for high dimensions. So if I take the limit p going to infinity of the volume of the ball of radius r, then this is 0. Okay, so the balls are shrinking away. Okay, I mean, and of course we can give estimates how big they are. But very often, I mean, one also wants to invert this somehow. So of course, I mean, if I make r bigger, then the volume is getting bigger. And let's say I want to keep, so I mean, I want to ask the question, so how big has the radius to be in p dimensions so that the ball has, let's say, a radius 1? So that it has more or less the same radius as the cube. And this means, of course, I must make the r also bigger and bigger in the dimensions. So one might also be interested to understand how do I have to scale r with the dimensions so that in order the radius, the volume of the ball of this radius has more or less 1. Volume 1. So this means essentially, I mean, this quantity, I should choose the r depending on p such that this guy goes to 1. huh? Okay, and I mean, if I bring this here under this here, this doesn't count. So essentially, you have to see that I have here balanced the r squared with the p. So the r should go essentially like the square root of p. And then I have a ball of more or less volume 1. A ball which has more or less the same volume as the unit cube. So maybe let me write down this here as the second part. So I mean that's usually estimates I want to make. I want to see that things are getting small, but on the other hand, maybe I also want to see how should I consider the dependence on some quantities on the dimension so that they keep more or less the same size. And that's something which we can see here in a very basic version. So in order for the ball of radius r in dimension p to have volume 1, so this means to have the same volume as the cube in this dimension, we have to scale the radius also with p. So the radius has to scale with the dimension. And the main thing is that essentially this quantity here is of the order 1. So this should be 1. So r squared should be 1 over this. So it should be p over 2 pi e. So r should behave essentially like the square root of p, but maybe we can also a bit more precise say like this. Good. Okay. And yeah, I mean this is a maybe this is a strange behavior that the volume, I mean, okay, let us look on the unit ball, that the volume of the unit ball really shrinks away in high dimensions. And maybe it's even more surprising because in low dimensions, it's the other way around. So I mean, first the volume increases up to some point, and then only it goes down. So namely, if you write down the volume of the unit ball for small dimensions, it's not that it goes directly to 0. So I mean, if we compare 1, 2, and 3 dimensions, we see that the volume grows. Okay, but this is totally different in higher dimensions. So maybe if I have p and the volume of the unit ball, so in dimension 1, so what is it? There it is 2. That's just the interval from minus 1 to 1. Then in dimension 2, it's the area of the disk, which is pi, which is bigger than 2. So okay, and then in dimension 3, it is for pi over 3. Which is something like 4.19, which is still bigger than pi. In dimension 4, it's pi squared over 2. I mean, we have the formulas, we just have to use them. And this is something like 4.993, still increasing. And then at 5, that's the maximum. In dimension 5, the unit ball has the biggest volume. Okay, I don't know. There's probably no reason for this, but it's strange. Okay, so 5, it's 8 pi to the squared by 15. So this is about 5.24. And then it's going down. So in dimension 6, it's 5.17. So it's going down, and then it's going down, and in the end, it's going down very fast to 0. So somehow it's like 2, 3, 4, 5. So it's here, it's 2, then it's pi, it's going up a bit, okay, and then it's going down. So if we are in small dimensions, and even if we would have a good picture of maybe even 4 and 5 dimensions, we still would get the wrong picture, the wrong idea how the volume of the unit ball behaves in high dimensions. Good. Okay. So that's the first step. But this here is, of course, maybe now this is just the volume of, let's say, all the things we are interested in. No? So I mean, let's say we are interested in the unit ball, and then of course we should normalize the volume of this to 1, and then we can ask questions about maybe vectors in a unit ball. And that's the real questions we want to ask. I mean, this here is just our, let's say, our whole space. And of course, in different dimensions, the volume is different, but this means the normalization constant is behaving maybe in a strange way, but still we can say, okay, the unit ball, that's the guy in which we are interested, so we normalize this to have volume, or maybe let's better say probability 1 in each dimension. Which means we just have any question we ask, any volume we consider, we have to normalize it by this guy here. And now we can ask questions. So namely, now we can ask about this concentration phenomena. So and this means now we are looking on maybe let's say vectors in the ball which may be sitting somewhere or have some property, and what is the probability of them. So what is the volume of those guys compared to the volume of the ball. And we have concentration, so many properties really concentrate somewhere. And so maybe that's this random vectors in the balls in high dimension concentrate, and maybe there are a couple of slogans. Maybe let me just write down the slogans, and then I want to prove them, be more precise about them. Okay, but of course, I mean, there is this slogan that the volume in high dimensions actually is also concentrated in a very small part or thin part of the ball, namely it's concentrating at the surface. Again, something which we don't know, which we don't see or from small dimensions, but in high dimensions, more or less the whole volume is sitting close to the surface. Okay, then there's also that if you look on the equator, the whole mass is more or less sitting at equators. And maybe if you're comparing two vectors in high dimensions, they are more or less orthogonal. Okay, so those are things which happen in high dimensions. So I want first to formulate them in an informal way, but then we will talk more about them and also to see how to make such statements precise and what we really mean with this. Okay, so those are maybe the main 3 concentration things you can say about concentration in the balls in high dimensions with respect to the volume. And they should give us an idea how to make them precise, but also how to prove such things, or what do we really want. And for the ball here, I mean, here we have the formula for the volume, so we can more or less calculate the quantities which we want, and then of course we can either see how do they behave asymptotically, or maybe better we can do an estimate, so that we have estimates for probabilities that we are close to something. So those are things which I want to make clear in the following. So maybe today I just write down the slogans, and then next time we are really going to prove them or parts of them. So those are phrases which one very often sees about high dimensions. So in high dimensions, and so we are talking about our balls, the volume of the balls, and then the volume of a ball is actually concentrated close to its surface. So the volume of the ball is concentrated close to to its surface. I mean, this is something which is quite easy to see from the formula for the volume, but then maybe something which is maybe even more counterintuitive and maybe a bit harder to see, but still we can do this. So almost all of the volume of the ball lies near its equator. Of course, maybe I should say what do I mean with equator, in particular in high dimensions. All of the volume of the ball lies near its equator. And one should, I mean, equator is okay. Maybe in a ball, I mean, you think the equator is the one which corresponds to, let's say, the North Pole. Huh? Equator is essentially, in the ball, it's a surface which goes to zero. Huh? So it's a plane which goes to the point 0 and which is orthogonal to one vector. Huh? And I mean, usually the one vector is the North Pole. So the equator is essentially what is in this circle, but actually I mean also the interior. So if I'm talking about the ball, I'm talking about also the interior of the ball. So the equator is also, it's just the disk which goes through the point 0. Okay, and okay, the disk itself has no volume, but I mean if I take a small slice around it, then that's what I mean with most of the mass is there. Okay, and then maybe, so I will be more precise. I mean, more or less we are going to prove this. Actually, this will also show up in assignments. So today there will come out first assignment sheet and there will be more about this. Okay, but maybe also something which we have in high dimensions is that any two vectors in the unit ball are almost orthogonal. Also something which is not true in small dimensions, but in high dimensions, I mean, if you take two vectors at random, then you can be quite sure that they are almost orthogonal. The ball are almost orthogonal. Good. Okay. And so maybe let me just draw the picture. So what am I really saying here? And in particular, if I'm drawing the pictures, they are pictures in small dimensions, where of course those things are not true. Huh? So I mean, I want to show you via pictures in small dimensions things which those pictures don't satisfy, but still they should give you some idea. Huh? Okay. So I mean, the first one. So I mean, if I'm so I have here in 2 dimensions, I have the disk, and of course, I mean, my volume is somehow spread over all the disk, and of course, there is sitting a lot of volume also close to the middle or so. But in high dimensions, I mean, the point is, the statement is that more or less all the volume is sitting in a small shell around the surface. Huh? Okay, so I mean, so I take here a very small part. Let's say I go away epsilon from the surface. So I have an epsilon slice, and more or less all the volume is sitting there in high dimensions. Of course, in 2 dimensions, not so much. I mean, not so much area is sitting here compared to what I have here. But in high dimensions, more or less everything is sitting there. Okay. So another slogan is: if you are peeling an orange in very high dimensions, nothing is left. Because it's all in the surface. Good. Okay, then maybe let me also draw a picture about the equator. So maybe the equator for this, maybe I should try to draw a 2-dimensional version of a 3-dimensional picture. Okay, so that's here my ball. And the North Pole is, let's say, here. Okay, and then the equator is what is cut out here. So, and the statement is most of the mass is sitting close to the equator. And now I'm talking about the ball, not just about the surface. So with equator, I also mean all the interior stuff here. And then, of course, I have to take a small piece along this with, let's say, with epsilon. But this can be very small. And then the statement is that most of the mass is sitting here. Okay. And of course, in higher dimensions, of course, it's the equator is a p-1 dimensional object. So it's something which is orthogonal to one vector. Or you can say maybe here, those are the guys, I mean, the equator itself are the guys where, let's say, the third component is equal to 0. And then close to the equator means the third component is very small. Maybe then it becomes more obvious that this might be true. Okay, but here, of course, not so much mass is sitting here. And in particular, I mean, you are free to choosing which equator. Because, I mean, you're choosing, I mean, this is the equator corresponding to the North Pole, but you can also take, let's say, the East Pole, and then you have an equator which is orthogonal to this. So I could also consider, let's say, here, this is my East Pole, whatever this is. And then, I mean, I cut my thing like this, and I consider a small slice around this, and then it's saying all the mass is sitting here, which is also not true. But the statement is it's sitting in all those equators, so in particular all the mass should also sit in the intersection of those two guys. And this is of course totally ridiculous, because the intersection of those two guys is very small in the low dimensions. But in high dimensions, the intersection is getting bigger and bigger. So I mean, yeah, the mass is more or less sitting in those guys. Okay, yeah, and I think I will stop here today. But next time I will then make those statements more precise. So I mean, first of all, we really should see what do I mean with this. So I mean, I'm talking here about probabilities that something happens, and probability is essentially, of course, in this setting is the volume of where I have some property normalized by the volume of my ball. And so I have to see that I can estimate those volumes and see that they here I'm claiming concentrated close to its surface. So this means the probability that I'm close to the surface is very close to 1. Okay, one can do this asymptotically, but better is to have estimates by saying I can estimate the probability how close it is to 1. And that's what we want to do next time. Yeah. Okay, but in the assignments, which should come out today, I mean, there's also some things around those concentration ideas. And so, I mean, we will be more concrete, and we will have much more to say about those in the coming weeks. Okay, thanks. That's it for today.